ممكن. Okay, great. Bismillah, alhamdulillah, salatu wassalam, Rasulullah. So we will continue differential evolution technique, which is the global optimization technique, different than genetic algorithm in the way we implement mutation and the crossover. We already covered some of the steps of the technique. And as we mentioned, the initialization step is similar to genetic algorithm. You start randomly scattering all the possible solutions over the search space. And then you can find out what would be best solution. And this is why we are looking for. Let me convert it to presentation mode. And then mutation, we have different forms of mutation, as we discussed last time. And you can use any one of them, and you can either this one or the first one, you can do the mutation. And after the mutant vector being formed, you need to create the trial solution. If this is the range of F, and randomly select this. So different differential evolution algorithm, you have the crossover to create the trial solution from the parent and the mutant vector here, or VI. So you have VI and XI, XI is the parent, and then you create the trial solution with the crossover factor equal to some kind of 0.5 to 0.9. So if you create a random number, if the random number is greater than crossover, then you take from the parent, or opposite, the opposite way, it doesn't matter. You have crossover, if it is set to 0.5, so it doesn't matter if it is greater or less, you pick from one of the XI or VI. So this is the rule. If its value is less than the crossover factor you set, the parameter value is taken from the mutant vector. Otherwise, you pick from the parent. So simply you can say any parameter in the trial solution equal to the parameter of the mutant vector, or the parameter of the parent, depends on a random number you create between 0 and 1, and you compare it with the crossover factor here. Okay, so this is the way to implement the crossover. For each parameter, you generate a random number. This is should be set at the beginning of the code, crossover factor. But for each parameter, you create a random number and you compare it to the crossover factor, and then if it is greater than, you select from the parent. If it is lower than, you select from the mutant vector, and then you go for the other parameters. You loop here, if no, until you finish all the parameters in the vector. Okay, and then you can go to the other vector, next vector. And again, you start from here, and then you continue. So this is the parent vector and this is the mutant vector, VI, and this is a trial vector that we need to create. So depends on the random number and the crossover factor, you can pick the gene from the mutant vector or from the parent. So you create the trial solution here or trial vector. The next step is to compare between trial solution and the parent. And the winner will go to the next population. So if the crossover plays, of course, the convergence, crossover becomes very small, it becomes very probable that the trial solution could have characteristic of the parent vector. As we mentioned, the typical range between 0.5 to 0.9 in order to avoid any slow convergence. Selection, you compare between the trial solution and the mutant and the parent. Trial solution and the parent. And the winner will go to the next generation. Select the better one for the next generation. So the vector that will be coupled to G+1 next generation, either the trial solution or the parent solution, generation G here. So if the fitness, I'm assuming this is minimization problem again. If the fitness is lower than fitness of the trial solution, is lower than the fitness of the parent, then we can say the trial solution is better than the parent. So we will take it for the next generation. Otherwise, we will take the parent if the opposite occurs. The stopping criteria is not different from the evolutionary programming or from the genetic algorithm. The same stopping criteria can be implemented here. The search will terminate if one of the following criteria is satisfied. The number of generations since the last change of the best solution is greater than or this solution is greater than a specified number. And the best solution doesn't change for a long time, then you can stop your search. The second is the number of generation reaches the maximum allowable number. So in this case, you can stop the search. Of course, this is not recommended. No, as far as the problem is improving, and you can allow more, and don't stop the search here. This is G maximum. If you relax it, usually when we face such a problem, and a number of iteration or number of generations hits the maximum number, then you can go back and reset the Gmax. You can relax it more. Gmax, you need to relax it, open it. This will give you a better result or a higher quality solution. عندنا هشام محمد. Do you have a question, Hisham?
Yes, doctor, I wanted to ask about this condition about the selection step. This is based on the minimization problem rather than the maximization. Am I right?
Which one? Second?
To select
this one?
No. The step selection.
Oh,
step number 4.
Yes.
Yeah, we have here condition to just.
Yes. The default is a minimization. كل كلامنا all our discussion will be assuming that we have a minimization problem. So if the fitness of that solution is less than, or the objective function of this solution is less than the objective function of the parent, that means this is better than this one. So we will select it. Okay, we will copy it to the next population. Otherwise, we will keep the parent with us for the next generation. Is it clear, Hisham?
Yeah, thank you, Doctor.
So in case of you hit the maximum number of generation in any optimization problem, so that means you can get better result, but if you relax it more. Okay. So what are the parameters of the differential evolution here? What are the parameters that we need to set at the beginning?
The F parameter?
Yes. Parameters of DE.
Aren't they similar to like population and
Population A. Population A size.
yes.
Okay, you have to set the population size. Definitely you need to set the population size 10, 20, 50, or whatever. Nasser Hakami?
We need also to set the F between 4 to 0.9.
Mutation factor you have to set. Mutation factor. You need to set the mutation factor at the beginning. And this will be constant throughout the run. What else we need? Nasser,
Stopping criteria.
ليه? I didn't hear.
We should set the stopping criteria, am I right?
Yeah, the stopping criteria, you need to say we need to set the G max, maximum number of generation, and also we need to set the B max, the K max, let us say. What is the K max? This is the maximum number of iteration or generation where the best solution doesn't change. Okay. So this is the K max, and the maximum number of generation is G max. What else? There is another very important parameter that we need to set. Muhammad Tahir.
The crossover.
Yes, crossover.
CR. Yeah.
Crossover factor. Crossover factor. We need to set also crossover factor, and we keep it constant throughout the run. So these are the parameters of the differential evolution that we need to set at the beginning. This is similar to genetic algorithm. And this is also Gmax and the Kmax. This is also general for all the techniques. So we end up with two major parameters that we need to set, which is F and the CR, mutation factor and the crossover. So these are, and you can say that these are the only parameters in DE that needs to be set. And you can experience that And DE even is robust in terms of F and CR. If you change F in the recommended range from 0.5 to 1, or 0.4 to 1, and this one also from 0.5 to 0.9, if you implement this, you will see the differential evolution is performing very well. So it doesn't change much with these factors, these two parameters. So population size, the F mutation, and the crossover factor that we need to set. And this is the computational flow chart of the differential evolution. And I found it, good to. So you have here the population. Maybe you create this at random at the beginning, okay, and then you apply the mutation here, VI equal to XR1 plus F and so on. R1, R2, R3 are integer random number between 1 and number of population size. You select 3 randomly, and then you create a VI. And then you do crossover. Okay, this is the mutant vector, and this is the parent vector. So you do crossover. This is the crossover factor, CR. And then you create the mutant, the trial solution here. So this is a trial solution after crossover between the parent and the mutant vector. And then you compare the trial solution with the parent solution. So this is a trial solution, and this is the parent, which one gives you better objective function, assuming in this one is more, the fitness of this one is higher, or it gives us the minimum or lower objective function for the minimization problem, then we select this one. Otherwise, we will select the parent, and then we go to the generation +1 and so on. You create and you circulate here. So this is again what we described earlier. So this is the differential evolution.
Doctor?
Yes.
Just a quick for the last slide.
Okay.
That means I will do only. I have D1 all the way to DN, for example, or population size. Then after that, I will stick only to one vector that I can rotate in this circle. Is that right? Yani after getting the G+1, what will be the next? Yani we'll stick onto this vector and then keep.
Again, Fauzan, similar to genetic algorithm, you can either do the process as a batch, we are going together, or you can loop. And you can take VI, select 3 randomly, okay, and then you create a VI, and then you create a VI with the XI, and then you do crossover, you have this trial solution, and you compare, and then so this is one, and then you circulate all over until you finish the number of population, and then you start again with the mutation of this. Mutation will not be carried out based on this population. This is the old population now. You create here new population. Okay, you fill here. Okay.
Yes.
So you create here new population and you implement the mutation and so on. Or second approach is to do the batch. Let us do mutation for all this. Now we need, for example, this is مثلا 10 solutions that we have here. So let us create 10 vectors here. Okay? We create 10 vectors here. Is it clear?
Yes, yes, yes.
And then the parent and the corresponding vector, then we create a trial. And then we create another trial. We create another trial, and we create another trial, and so on. And then we go and we compare each trial with its parent, and the trial parent, and then you have here 10 solutions that will be selected as a batch. So, and you go on. But you can do this. And you can do, for example, for loop from 1 to 10, مثلا here 10 solutions, to do VI. Okay, VI then and the end for. Is it clear? You create here the mutation, and then you start another for loop to do the trial solution. You create a trial solution, end for. So you have all the trial solutions here. And then you do this comparison. So you have four from I1 to 10, from 1 to 10, and then you compare. And either you select this or this. So at the end you have here, end for, you will end up with 10 solutions here. Right? Is it clear, Fawzan?
Yes, yes, sir.
The other way is to take only one for loop. One for loop from 1 to 10. You do mutation. You create VI. You create a trial solution. You compare with XI, and you select. You select.
Yes.
And then you end. So each selection will give you one by one. And you have here one. If you finish this 4, you end up with 10 solutions. Yeah. You can do it either way. It doesn't matter.
Yes, clear.
Okay. Any other question? طيب. Okay, there was a proposal to give you just in a few minutes the some background on time domain response for second order systems, or usually any system can be represented by second order system. We will see the response of the second order system. Even if the system is with higher order, you can still approximate it. And even with higher order, you still have some dominant pools here. These will govern the response of the whole system. So just in 4 slides or so, we can see if we have, for example, the eigenvalues or the pools are here. So in this case, we have the over damped response, and of course the pools are real, so we don't have any oscillation. So this is the steady state. This is the steady state value. Okay, so the response of the system will start as such and approaches the final value without any oscillation. And the eigenvalues here are lambda equal to -2, lambda 1, lambda 2 equal to -3. So these are real. There is no imaginary part. If there is no imaginary part, but there is no oscillation for this mode. Okay. لأن this is J omega and this is sigma, real part and imaginary part for the eigenvalues. If there is no imaginary part, that means there is no oscillation. The response will not oscillate around the steady state. It will approach the steady state. But here you can see here no response is a little bit slow, and it will reach the steady state, but with long time. If you have this case where you have طبعا zeta, as we mentioned, the damping coefficient for these poles, if this is the case, the poles are on the imaginary part. There is no sigma here equal to 0, lambda equal to plus minus j, مثلا, for example, 2, and the sigma equal to 0. In this case, you can see here the response will zeta here equal to 0. That means there is no damping at all. The response here is not stable. It is oscillatory around the steady state value. And you can have here the response as such. It oscillates without damping. And this peaks are not going to be damped here. So constant oscillation, and you can see here the zeta equal to 0. So I have several hands on. Hisham Muhammad?
Yes, doctor, I have a small question.
Yeah, go ahead.
When we have the case 1, which is only the real number what we have, the zeta will be greater than 1 or equal to 1?
Zeta is greater than 1. Here for overdamped, zeta is greater than 1. Okay? Critically damped. Then V zeta equal to 1 when we have these two poles are coincide to each other. At the same location. Here, lambda 1 equal to lambda 2. We will see it in this case, Hisham, اللي هي critically damped, where zeta equal to 1. Okay?
Okay.
Nasser Hakami?
Yes, doctor. When we say this is, we are talking about the controller response, yes?
Yes.
So if this one is a frequency response or
let us say system response. Okay. You are questioning whether it is frequency domain or
no. The control this one, for example, on the governor side of generator, or which controller this one we are talking about?
This is the second order system in general. يعني ممكن يكون السكند اوردر سيستم ده فيه كنترولر او ما فيهوش كنترولر، ممكن يكون اوبن لوب سيستم او ممكن يكون كلوز لوب يو هاف كنترولر وات ايفر. يعني this is the system response whatever the system components is. This is the system response. لو انت عندك كنترولر, if you have a controller here and you designed it, probably the system and the system without response was unstable مثلا. This is without. With, you have a system stable. Okay. This is the system response. Whatever you have a controller or you don't have a controller, it doesn't matter. So if you have a system, a plant, and you do step input here, okay, this is the response. Assuming this is a second order system, and if you apply step input here, then this would be the response. This is overdamped. We will see here oscillatory. So you have here the oscillation, continuous oscillation. There is no damping, and the peaks are the same. Okay. So this is the case here. This is the plant in general. For example, Nasser, if you are talking about bar system, يعني assume that this is the synchronous machine and this is the mechanical power, VM. B mechanical, okay? So if you apply B mechanical to the system, you know what the case for the power angle and the time. You can see here, this is delta 0, this is the initial. If I apply step input, so this is the delta steady state, it will increase here, and then the response will be as such. The response is stable, so we will have such a response, okay? Or you can have of overdamped, the response will be approaching the steady state as such. So this is, it has nothing to do whether you have a controller or not controller. This is the system response.
Okay, clear. Thank you, Doctor.
Okay. So this is the case. You have here undamped case, zeta equal to 0. For this case, which is stable case, you can see here you have some damping, lambda here 1, 2 equal to sigma plus minus j omega. So we have an oscillation, and we have here the imaginary part of the eigenvalue. So we have oscillation, and we have also damping, and this sigma is negative here. So the response would be as such. So you have here maximum overshot, and then this peak is lower than this peak, definitely. Then we have some damping, and we approach the steady state. And this is system is stable, and these eigenvalues are in the left-hand side. We will discuss if we have the opposite now. But this is called underdamped case, where we have zeta equal between 0 and 1. So this would be if we have the eigenvalues here. If we have two eigenvalues where they are coincide to each other, then we have zeta equal to 1, and this is the system will be critically damped, or zeta equal to 1. As you can see here, for critically damped is faster. Response here is slow response if it is overdamped. And you can have the system is overdamped, you are there is no freedom for the system to overdamped okay. So overdamped is slow response. Here you have it reaches to the steady state value faster than the overdamped. You allow here for underdamped system to go over the steady state, to oscillate around the steady state. But this is the underdamped here. So if these eigenvalues are here, what would be the Abdullah Yusuf? Do you have a question, Abdullah?
Yes, in the undamped case, where is the steady state value?
حتى لو steady state value here, the steady state value, or you want to see where the steady state value, it oscillates around the steady state value without any damping.
So it is in the middle of the sinusoid.
Yes.
Okay, thank you.
So if we have such eigenvalues here, what would be the response?
Unstable. بيصير exponentially increase.
Unstable. طيب, if we have, طبعا this is the case, okay. If we have these eigenvalues are here, two eigenvalues at the right hand side, what do you think the response will be? What do you think? Salim, do you have a question, Salim, or answer?
No, just for this question, the response will oscillate increasingly to infinity, so it's unstable.
Oscillate?
Increasingly till infinity.
So it will go as such, then and so on. Okay. Term for this case is similar to what we have, it's unstable as such. So this is the step response of the second order system. This is also gives you how zeta will affect the response. If zeta is low and low, then you have the oscillation is higher and higher, or the maximum overshot here is higher. So as you increase zeta, as you increase the damping, then the overshot or undershot or the deviation will be much less. For zeta equal to 1, this is the critically damped, and for zeta equal to 2, it's over damped. As you can see, this the system response is slow. So this is usually the case. If zeta is negative, then the system is unstable. Some of the time response parameters here is important to shape the system response. And you can use these parameters in order to design your controller, and you can have to evaluate your controller based on these parameters, such as delay time, rise time, peak time, settling time, and this is the maximum overshot. So definition of the delay time, the first time that the response reaches to 50% of the steady state value. This is the delay time. Of course, if you decrease the delay time, that means a response is faster. Rise time, the time where the response moves from 10% to 90% of the steady state value. So this will also give you an indication of how fast the response is. The peak time is the time where the maximum overshot occurs. So this is the maximum overshot. This is the steady state value, and this is the maximum value you reach here. So this is the deviation or the maximum overshot. Of course, you can get it as a percentage of the steady state value. The settling time is the time where the response goes into a tolerance band of 2 to 5% and stay there. And if this is a 5% around the steady state, and this is 1.05, and this is 0.95 of the steady state. So the system response is going ups and downs, and then at some time it crosses here the bounds of 5 plus minus 5%, and they stay there. So the response is within this tolerance. This is the settling time. This is called here is the settling time. If you select 2%, that means you have very narrow band. So you may have of course, you can shrink this bounds to 2%. So this will be assuming that the response will cross the boundaries of the 2% and stay there at that time. So settling time. Of course, we need to have a settling time small in the time response. Then this will reflect you the transient period. The system will, the smaller the settling time, the better the response, and also the deviation. Definitely, you don't need a high overshot, and sometimes you can destroy something. Have mechanical, and you increase the speed of the motor or speed of any device 10%, 20, 50%, it may destroy the device. You need to minimize the overshot. You need also to minimize the settling time. You need to reach faster there to the steady state. You need to minimize the delay time. You need to minimize the rise time, and so on. So this is the definition, and I think we already covered this. Let us go similarly to what we have discussed earlier in the control problem. Time domain eigenvalue. Now we discussed there eigenvalue based objective functions. We can also define some of the time domain based objective functions here. The first one is called integral of the square of the error, where you have here, this is the integral or the summation. Of course, if you solve numerically with the step size, you can do summation of e square the deviation or error. You have a steady state. You have, for example, if you have speed, you have the speed and the steady state speed. So this is the error square. You need to minimize this deviation. Square طبعا لانه you need positive value, whether the speed is higher than the steady, the deviation is positive or negative, you need to consider both. This is the square root here. You can do the same, but instead of squaring this, you can have the absolute value of the error. This is also could be whether the error is positive or negative. You can take the absolute value here. This is generation or summation. When you solve this, and for example, you need to simulation time, T simulation equal to 5 seconds, for example, and you have a step size delta T or sampling time equal to 0.1 second. In this case, you will carry out 50 iteration. So you come here from I equal to 1 to 50 iteration. At each iteration, I will calculate the error square or the magnitude of the error, whatever the the objective function you can consider. So at each iteration, in your numerical solution, you calculate the error. Either you get the absolute value or the square, and you add them up for all iterations. So to calculate this objective function. Another is to incorporate the time here. You get the integral square of the error again, similar to this one, but you multiply this by the time. And this is very important. And if you multiply this by time, it means that you will force the response to minimize the settling time as well. Not only the deviation, but also the settling time. Where you penalize here the error, if the error occurs, and if the error occurs here at higher time, then it will be penalized more. Any deviation with the longer time, this will be penalized more. So this performance index or objective function will force to reach to the steady state error, to the steady state value in shorter time, and the time is involved here. Of course, you can also multiply t, multiply by this, so you have time weighted also absolute value of the error. So such objective functions can be used if you have a dynamic system and you need also to design a controller or something like this, similar to what we have in our case. You have KC, you have KT1 and T2, and you need to now not only not depending on the linearized model, you can use the nonlinear model of the system to simulate it, and you simulate the nonlinear model of the system, and then you have your objective function J, one of those. You can have it one of those. So this is your objective function of this. So in this case, you don't need to linearize and so on. And this is for nonlinear time domain simulation. Salim Ghanim, you have a question, Salim?
Yeah, Professor.
Yes, please.
Regarding these metrics, so can we say that incorporate the time error that we are minimizing the settling time and overshoot in the same time?
And I hear some and I don't hear some of your words.
Yeah, there is.
Can you repeat, please?
Yeah, it's regarding the time incorporation of the ITSE, for example.
Yeah.
Can we say that it works on the settling time and overshoot as well at the same time to minimize both settling time and the overshoot magnitude?
Yes. This is the overshoot, or this is the deviation, and this is the settling time.
Okay, so it's as if we have multiple objective in this case.
Yeah, and you can say this.
Okay.
And
Okay.
here, if the deviation occurs at t equal to 2 seconds, this will be, weighted more if the deviation occurs at 0.1 second. Okay? Yeah. So any deviation here would be multiplied by 2. Here would be multiplied by 3. So you are putting more weights for any deviation occurs at the end of the long time. This will force the. Of course, in terms of multi-objective, you can even, as we pointed out there, for the eigenvalue based objective function, you can have objective function based on sigma and the objective function based on zeta, and you can combine them. But be careful when you combine the for example, if you calculate this ISE, for example, okay, this ISE, لأنه deviation, فممكن الديفيشن وسكوير and so on, you can find the order of this ISE for the simulation time and all these iterations. You will end up here with, for example, equal to 0.25 مثلا. When you use such case or such performance index, since you are multiplying by time at each iteration, you see, at each iteration you multiply by 2, by 3, by 4, and so on, with the time, the simulation. So the order of this objective function, for example, could be 40, could be something like this. When you combine these two objectives together in one objective for multi-objective optimization, you have to be careful. You have to multiply this by a scaling, or you multiply this by a scaling factor in order to have the same order in the objective function. Salim, again, you have a question?
Okay. No, thanks, Professor.
Okay. So I think that this is what we can say about the dynamic or time domain simulation. Okay, so let us move to a new technique, which is particle swarm optimization. Particle swarm optimization is a little bit different than the previous techniques. We discussed 3 techniques so far: genetic algorithm, evolutionary programming, differential evolution, and these are based on survival of the fittest. And actually, all are based on the survival of the fittest. But here, a little bit different. Particle swarm optimization, it is a nature-inspired communities, societies. Here, we are not talking about mutation or crossover, but we are talking about learning process. If you assume that we are learning together, so you can depend on 2 factors. One factor depends on yourself, self-learning. This is, we can call it cognition part. You need to learn from your own experience. Okay, and you have several, take several decisions in a certain matter, and then you learn from your own experience. And the second part is you also learn from your neighbor or from the society experience. You learn from others' experience. So the learning process here has 2 components. In order to improve your situation, you learn from your own experience, and you learn also from others' experience. You have some social part, and you have also your cognition part. Okay, so the technique here is a little bit different than the others, and this is not only the particle swarm, but the swarm intelligence in general. We have several techniques under this umbrella. Particle swarm is one of them. You can have ant colony also, which mimics the ants behavior, and also the artificial bee colony, also in searching and performance behavior of the bees. And also there are other techniques under this umbrella. You have here some kind of learning process, and this learning process has 2 components: one cognitive and the other social part. So this mimics the birds, fish, ants, and all these communities or societies. So we will see the overview and particle swarm optimization. We will give you some definitions of the terms that we use here in particle swarm. And also we will see the algorithm in steps 1, 2, 3, 4. Initialization, which is similar to what we have in genetic algorithm. And velocity also, we have here particles, and we assume here these are the particles, and each particle here in this technique specifically, each particle has velocity. position and the velocity. Okay, so each particle here x has a velocity v, and this particle will fly in the search space. This is the search space. This is x should be greater than or less than and so on, x1 and x2. So this is the search space. So this particle will fly around here, will move within this search space. But how this particle will adjust its position? Each particle has its own velocity, and this velocity will be updated from iteration to iteration. And based on this updating of the velocity, this position will move somehow here, 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 and so on. It will move around until we have the how this particle updates its velocity. This will be discussed in detail. This is where we are talking about the cognitive part and social part. This particle adjusts this speed based on its own experience and also based on others' experience. So he can get which direction we should go. So after the first iteration, it will be here. After the second iteration, it will be here, and the third, and so on. So velocity update, which is a major step here in the particle swarm, how to update the velocity. And definitely, if you have the velocity and the position, then you can update the position, assuming that the time is one, then iteration after iteration. And then stopping criteria, which is similar to what we have discussed in other techniques, nothing new here. And we will see the parameters and how to set the parameters of the particle swarm. So particle swarm is introduced in late 90, actually in 1995. And you can see here the combination. It's invented by Eberhard, engineering professor, and James Kennedy, social scientist. So they are merging the engineering and social, science. So PSO technique combines social psychology principles and socio cognition, human agents, and evolutionary computation. So it is a combination, as we mentioned, between the experiences, your own experience and the others' experience. So a particle swarm has been motivated by the behavior of the organisms, such as fish schooling and bird flocking and ants and so on. Generally, particle swarm is characterized as simple in concept, easy to implement. It's very easy, just one equation for velocity update, and computationally efficient also. When you compare it with the genetic algorithm, for example, you will see it's more efficient, and it balances between local experience and global experience. Usually, a genetic algorithm, it's global search technique. Maybe we classified the techniques earlier at the beginning of this course. We classified the techniques as a global search technique and local search technique. Local search technique, such as taboo search and simulated annealing and so on. This particle swarm balances between global search, genetic algorithm and its family, and also local search, which is the taboo search and others. So it is balances between the global and local search. Yes, here it is. Particle swarm has a flexible and well-balanced mechanism to enhance global and local exploration abilities. Like any evolutionary algorithms, Particle swarm technique conducts search using a population of particles. Again, a population-based technique, and you are handling 10, 50 solutions together from one iteration to another, corresponding to individuals, each particle corresponding to a chromosome and genetic algorithm, chromosome corresponding to a solution of the problem. This is the particle. Each particle represents a candidate solution of the problem. In particle swarm optimization, particles change their positions by flying around the search space until either condition is satisfied here. This is a stopping criteria. A relatively unchanged position has been encountered. Yani this solution doesn't change for a long time. So you can stop the technique, or the computation limitations are exceeded, yani maximum number of iteration is hit. A particle swarm system combines a social only model and the cognition only model. Yani you combine social part and the cognition part together, as we discussed earlier. The social only component suggests that individuals ignore their own experience. They are not relying only on the behavior according to the successful beliefs of individuals in the neighborhood and others' experience. This is a social part. On the other hand, the cognition part component treats the individuals as isolated beings, and you are learning from your own experience. A particle changes its position using these models, both models, as we will see later on when we talk about the update, the velocity and position. Unlike GA and the other heuristic algorithms, PSO have the flexibility to control the balance between the global and local exploration, as we mentioned earlier. We have these two parts. This is the global, and this is the local. Cognition, the local, and the global is the social part of particle swarm. This unique feature of PSO overcomes the premature convergence of GA and others and enhances the search capability. You can see the importance of the collaboration among the particles, among the solutions, among the individuals. These are the techniques that could be under the umbrella of swarm intelligence, particle swarm and colony, and artificial bee colony, and also artificial immune system algorithm. If you have here, this is a bond or some kind of, you can see here the fish is at the minimum point. And if you have two fishmen, here they are talking to each other, they are communicating where the position you are reaching, and you can see here, this one is moving, he find here the better, but this one is find the more better than this one. So this will, start, updating its position and moving around until it reaches to the optimal solution. So the basic idea is each particle is searching for the optimum. Each particle is moving and hence has a velocity. And each particle remembers the position it was in where it had its best result so far. So this is we call it personal best. And when you are moving as a particle or the solution was here and then it moves And this is position 1, this is position 2, this is position 3, and this is position 4, and so on. This solution will memorize the best location it was. So maybe to the personal best or local best or vertical best, let us say vertical best. This is the vertical best solution. So it should remember this, and this is the best solution that I found here. Okay. طبعا there are other solutions, they are also moving here and there, and this solution will remember its best, and also it will look at the global best. You have 50 particles moving around, so the one with the minimum objective, this will give you, assuming طبعا this is a minimization problem, this will give you the minimum or the best solution, so it will update the velocity accordingly. So the technique here has some kind of memory, and the technique, and this is also another advantage of vertical swarm, and it has a memory, and you still remember where is the best solution that you visit. And keep in your mind, and we are searching for the best solution. And we can move, if we hit a solution with better objective, plus we will assume it as the best solution, but it will not prevent us from flying, from exploring the search space. So we can keep the best solution with us over the iterations. But this wouldn't be much good on its own. Particles need help also in figuring out where to search, where is the best solution. And this is the particles in the swarm cooperate. They are communicating the best solution among themselves, and they exchange information about what they have discovered in the places they have visited. The cooperation is very simple. In basic particle swarm, it is like this. A particle has a neighborhood associated with it, the particles around it. A particle knows the fitness of each of its neighborhood and uses the position of the one with the best fitness. And it looks to the best solution or best particle, and also it looks to its own best position. I hope things are clear. If you have any question. So the particle will update its position based on its own best, which is called the particle best, as we mentioned before, and also with both, the particle can update its velocity and its position accordingly. The position is simply used to adjust the particle velocity. Some of the terms will be used here. We need to define them at the beginning. What is the velocity and what is the position? What is the particle? What is the swarm? And we will see the updating the velocity and the position later on. So the basic terms here, the particle is the solution x of t, and this vector of real valued parameters here has m dimension. The dimension is m, and m is number of optimized parameters. طبعا nothing new here. It is the same as differential evolution and others. Particle is a solution simply. At each time t, the particle j can be expressed as xg equal to the parameter 1, parameter 2, parameter 3, parameter m. So these are the particle. x1, for example, k, t1, t2. This is 10.2 or 0.5 and 0.3, whatever. So this is the particle. And these are the optimized parameters, and of course, you can have this dimension m of optimized parameters. The population طبعا هي a combination of the solutions, if a set of n particles. So population equal to the particle 1, particle 2, particle 3, and transpose. x1, x2, and so on. This is the population. And similar to what we are discussing earlier. Nothing new. So far, nothing new. The swarm is the population of the particles. And this is the population. What population? The swarm is population. Same. Same, but when we are talking about swarm, the swarm is population. Moving particles that tend to cluster together and seems to move in a random direction. Each particle will fly in a direction. If you look at these particles, you can expect that they are flying randomly, but actually they are trying to cluster with each other to the optimal solution. The particle velocity. This is the velocity of the moving particles represented by m-dimensional again. Velocity also is m-dimensional. And you have a velocity for the k direction. You have velocity in t1 direction. You have velocity in t2 direction. But this velocity definitely will be, and when we say k from 1 to 100, then the velocity definitely will not cover the whole. The velocity could be, for example, plus minus, could be negative, by the way, plus minus, for example, 10. So this could be minus 5, and this could be minus 0.01, minus 0.02, or plus. طبعا مش لازم كله minus. Velocity is different from one dimension to another. But definitely, velocity is much lower than the bounds here. Actually, we will see how to set the velocity later on. At time t, the particle v, the particle velocity vj, can be described as velocity in the first dimension, and in terms of k, velocity in terms of t1, velocity in the direction of t2, and so on. So Vj has m-dimensional also, a real valued vector. And this is the velocity component of the jth particle in respect to the kth dimension. It's okay. And this is the velocity of particle 1 in the dimension of first parameter. Hisham Muhammad, your question, Hisham.
Yes, Dr. Actually, I have this question. Can the particles be considered as the chromosome in the GA?
No. As I mentioned, and this is K. The K range of K from 1 to 100. You cannot allow this velocity to be from 1 to 100. Even if you start randomly. Each particle, if this is the search space, you are not allowing this velocity or this particle to jump to this one. Now this particle will move in like limited step. So it can move here for the first one, and then it move here, and you are limiting the movement of the particle. This is very also valid in terms of the community. Do you think in learning process of each one of us, the learning process in over the night, he becomes مثلا a brilliant man while others before learning process is still limited. Am I right?
Yes.
You cannot allow the velocity to be cover the whole range. So this is not a solution. The V1 is not a solution. The position هو the solution. The particle position this is the solution of the problem. Okay? So the velocity is similar to the chromosome in terms of the structure, in terms of the dimension. It is m-dimensional real valued vector, but it is not a solution of the problem. The velocity is not a solution. Hope it's clear.
No, Doctor, actually, could we go back to the previous slide?
More?
As you said here, the X1, X2, X3. Can we consider X1 as a chromosome, the GA?
Yes, this is a chromosome. This is a particle. This is a solution of the problem. The X1, إنما ال V, the velocity is not. The velocity is not a solution. The X is a solution. Did you get the point?
Yes, now it's clear.
Okay. Khalid Suleiman. Please, Khalid, go ahead.
Yes, Doctor. I just wanted to show the fact that the population seems to be changing at different times, as the definition suggests. It's not fixed. Population is not fixed, right?
Yes, population is not fixed.
So does this mean we at different times we are considering different populations? Maybe we are adding new solutions to the search space.
لا هو الفكرة ايه the idea here is the population is not fixed and this particle it was here. This is a search space. The particle was here. So you have a dimension here مثلا for example this is x1, okay, this is x1 مثلا for example. You have the k, t1, t2, 25, and this is 0.5, and this is 0.1. Okay, this is x1. And when you have the velocity of this particle is, for example, -2, 0.1, -0.05, for example. Okay, so you have a velocity, and you have this is v1 and this is x1. Now, this particle will update its position. It will update x1 prime or x1 at iteration 1. Here, x1, this solution in iteration 2 will be equal to the old position plus the velocity, v1. So in this case, you have x1, this particle will move to here. And here was 25 minus 2, so it is 23. This one will be 0.6. This one will be 0.05. So this is the new position for that particle. So this will be the new population. Okay, this will be new population. This will be repeated for all x2 here. You have here v2, and then you have x2 of 2. This is x2 of 1, or whatever iteration number counter, and then you move and so on. So you update the position according to the velocity, and you create new position, new particles, new solutions. So this is the solution which is different than the old solution here. Is it clear, Khalid?
Yes, it is very clear. Thank you, Doctor.
Okay. So, okay, let us. So velocity is not a solution, but it governs the position updating. And we will see how to update this velocity. Velocity is not constant. Velocity is directed by the particle best and the global best, as we will see later on. So, and the velocity is different, real valued m-dimensional vector. And you can see here the velocity is different in each direction. It depends on this limit on the velocity. Yes, here it is. The particle velocity in any dimension is limited by some maximum value, V maximum. It shouldn't exceed that value. As I mentioned here, we can have this equal to plus minus 10. This is the velocity maximum of k dimension, plus minus 10. So we limit the velocity here in k dimension to be plus minus 10. So and the other dimension as well. The time is over, Shabab. And we exceeded time by about 8 minutes. Are you enjoying it, or you are already left?
No, we are with you.
Oh, it was interesting.
Let us stop here, and if you have any question, then you can raise your hand and ask. Otherwise, you can